Hello and welcome. In this video I'm going to be covering the notes for the 2.5 section, which is covering over all the derivatives of trig functions. So parts of this video you may want to pause and just take notes of maybe like just the colored in boxes, or again you can also reference this inside of OneNote. But mainly I'll just be describing some of the things as well as working through the examples you see. So to start off, as you can see on the screen currently, we've got the derivative of sine, and if we needed to have a proof of what that would be, we could just go through and do that same process of the limit as h approaches 0 of that difference quotient, substituting x plus h in place of the x in sine, and then subtracting the function at x, so just subtracting sine, and then simplifying. And notice right about here to here things get a little bit, I guess you might want to call that a little bit creative, but they kind of just rearrange so that the factoring portion, those two end up just swapping position. That way we can get the two that have sine of x near each other, factor out, and then once we get it to where it's four separate things, as you can kind of see right there, two terms but four separate parts being multiplied or added, we end up having this portion, the cosine of h minus 1 all over h. That's one of the limits that we had with trigonometry from an earlier section that has a value of 0. And then we also get the sine of h over h, which popped up a fair amount on the last test, that its limit as h goes to 0 has a value of 1. And as you can see at the very bottom, we end up getting the sine of x from right here, then times 0 from here, and then the limit of cosine, or limit as h approaches 0 of that would just be the cosine on the inside, and then as mentioned that part turns into 1, which then turns into a 0 plus cosine, which is in fact cosine. So key takeaway here is, at least with this first example, I'm not going to go into as much depth on every other one, just wanted to kind of show what the process is that would allow us to like prove why these derivatives are what they are. Good majority of this is just going to be remembering if I see the derivative of sine, or I'm being asked to do the derivative of sine, it will always turn into cosine. So kind of my good rule of thumb with this is if it starts with a letter S or anything other than a letter C, the derivative of it will actually turn into something that has C to start. So sine will not just stay sine or become anything crazy, it's just sine turns into cosine, and as we'll see here in a moment, the derivative of cosine will turn into the opposite of sine, which again I could explain a little bit more when we get to that part of the video. But if I scroll down really quick, just to give you a visual of what those two graphs are, the sine graph again is the top one here, where it starts at the origin, goes to a high point first, a quarter of the period later. And notice that where the horizontal tangent lines exist, which if I try and highlight those a little bit more, like these horizontal tangent lines on this graph, notice for the derivative then must equal zeros, or x-intercepts, because again the derivative is representing the slope. So notice all of the highs and lows of a sine curve turn into the x-intercepts of its derivative, which happen to match this idea of the cosine function. Similarly, you can kind of see in the middle, as it's going through 0 right there, that it would have a slope that's approximately positive 1, which in fact it is exactly positive 1, which you can kind of see at the high point, it's why it's starting at 1. Then at this next one at pi, it's coming down the page, so hence why it's down here at negative 1, and it just keeps alternating back and forth between a bunch of positive 1s and negative 1s in between all of those high points and low points, and again it creates that graph of a cosine function. So let's actually try out a few of these derivatives, again just keeping in mind that the derivative of sine is just going to be cosine. Combine that with some of the older properties that we've learned, such as the power rule, the product rule, or the quotient rule, and hopefully we can get through all of these even though they're going to be intermixed. So like letter A, for example, I will just take the derivative of that, since it does ask for what is y prime, which is the notation for derivative. Y prime in this case would equal the derivative of x is just going to be 1 plus coefficient is just going to stay 4, and then times derivative of sine, well that's the new thing, that would be cosine. And voila, we've got our first derivative that involves some trig. hopefully not overly complex, but it did have a combination of the power rule with the first term, remembering what to do with coefficients, and then remembering now the derivative of sine will always turn into cosine. If I could simplify from there, I would go ahead and try and do so, but that's really as good as that gets. For letter B, this one has two things being multiplied, so for sure I'm going to have to use the product rule. Just as a quick little recap of product rule, if I had product where it was a times b, its derivative would end up being a times b prime, added with a prime times b, or whatever order you wanted to do those. I just need to make sure that I end up with an a times a b prime and an a prime times a b. I need those as my two terms that technically will get multiplied together. So for this one, I'm going to go ahead and call the x squared function my a and the sine function my b, and just follow that pattern. So y prime for this one is going to be, if I do a times b prime, well, that's the derivative of sine, which is cosine, plus, this time it's going to be a prime, so derivative of x squared, that's 2x, and then I multiply by the b function, or the sine function. And if I could factor or reduce, I would go ahead and do so. I'm actually thinking that's probably as good as it gets, but maybe you notice there is the ability to take an x out. Since they both have an x, I could say that that's really x times and then x cosine of x plus 2 sine of x. But the only time we really need to necessarily do something like that is if I was needing to do like an extra step like set it equal to 0, or if I recognize that when I factor, what's left on the inside actually has like a trig identity that maybe I can take advantage of. Move on to a couple more examples here. Sine of x over x. That definitely is two things being divided, so this will require us to do the quotient rule. And quotient rule, if I had that as like a divided by b, its pattern is going to be the b times a prime, so it kind of goes a little bit backwards from what we normally would start with from the product rule. So bottom times the derivative of the top minus the top times the derivative of the bottom, so a times b prime, then all over whatever the bottom is squared. So I'm just going to call the sine of x the a, and then the b, I'm just going to have be the denominator, which is just plain x. And now again, following that pattern I just identified, I've got y prime in this case is going to equal x times, and then now it's the derivative of sine, which is cosine, minus sine of x times its times the derivative of x on the bottom, which really is just like times a 1. So I can probably just drop that times a 1. In fact, I'm just going to erase that anyway. And then it's all over whatever the denominator is squared, which x times itself is just an x squared. Don't really have any simplifying I can do. So that's actually as far as I would need to go, unless you really wanted to split that into two separate fractions. Very last one. Here I've got e now involved, so a little less power rule. Now it's going to be the exponential rule. This is still, though, two things multiplied, so this is back to a product rule. So I'm just going to follow that same pattern as before. If I call this a and call this b, this is going to be ab prime added with a prime b. So let's go ahead and do so. This would be y prime equaling, let's do a, which is e to the x, times cosine, since that's the derivative of sine, added with, now it's the derivative of e to the x, which just happens to also stay e to the x, but this time times the original b, which was sine of x. And here I notice they both have an e to the x, so kind of like before, I would probably at least look to see if I can factor something out. If I can write e to the x fewer times, that should be better. And that leaves me a cosine of x plus a sine of x. Unfortunately, there is no trig identity I can use for that, so that actually is as good as it gets. Technically, the version right above this one would also be an acceptable response when it comes down to a test. Alright, moving on to the next derivative. We'll start with, now, what is the derivative of cosine? So cosine, if we were to, maybe scroll down a little bit more so we can see all this. Cosine's derivative, as kind of mentioned before, we could go through and do the showing of the why each of these derivatives works, but again, if I were to go through and do the same process, most of the work would be very, very similar. it actually would create a negative sign a little bit extra. So how I just remember it is basically any trig function that starts with the letter C, whenever I take its derivative, it's going to actually start with a new coefficient of -1 or just a negative sign on it. So if we can just remember that sine and cosine do kind of go back and forth amongst each other, the derivative of cosine will just be negative sine. So basically I just need to be able to recognize, kind of like with the last few examples, when I see a certain function, what its derivative will be. So kind of similar also here, I'm just going to identify other properties or rules I might need to follow. So like for this first example, letter A, I do have x squared times cosine, so this once again will be another product rule. And just because I don't think we can see it enough times, this would just be a times b prime added with a prime times b, and follow that pattern. So it's going to be for this one y prime equaling a, which is the x squared function, times b prime, so cosine of x, its derivative will be negative sine of x. So I might want to rearrange this so that negative sign gets protected a little bit, or I don't accidentally forget about it. Plus, then it's going to be the derivative of the a, so that would be derivative of x squared is 2x times, and then I keep b alone, or don't mess with it, so it's a cosine of x. So kind of like I mentioned before, just because that negative sign I don't really care for a whole lot being on that first term, I'm actually going to do a little swapperoo with these two and call this 2x cosine x, and then minus x squared sine of x, just so again that minus sign gets a little bit more protected. If you wanted to say it was negative x squared sine of x plus 2x cosine x, that technically is still correct. But again, it's kind of easy to drop some of those negatives if they're on the very first term, so I kind of recommend just swapping the order if need be and taking that negative with that term. So again, notice I put the positive one, the 2x cosine x first, and then just had a minus sign for that first one. If I go to the next example here, see if I can maybe give myself a little more room. There we go. This one looks like I need to do a quotient rule, this having both sine and cosine simultaneously, so this one will get a little bit more complex, I guess, at least with the new stuff. So this will be, if I follow the pattern, it's going to be the bottom function times the derivative of the top. So if I call this the a the top, the b the bottom, be b times a prime minus a times b prime all over b squared. So for this one, it will be g prime of theta being equivalent to my bottom function, 1 minus sine of theta, times the top function, the derivative of the top function, which is going to be negative sine of theta. Then it's going to be minus, now it's the top function cosine of theta, times the derivative of the bottom function. Well, I've got a negative sign, so that's actually going to be negative cosine. And then all over whatever the bottom is squared. So 1 minus sine of theta, all grouped up, and then squared. And I'm not going to worry about multiplying that out. I'm actually kind of hoping that maybe the top has something I can cancel out. So let's go ahead and distribute out the top. It looks like I get a negative sine of theta times a negative sine of theta for a positive sine of theta being squared. A negative sine of theta times the 1 will give me a negative sine of theta. So I kind of swap the order up, but again, foreshadowing that negative, I kind of want to have protected a little bit more. And then it looks like I've got a negative cosine of theta times a negative cosine of theta, which is a positive cosine of theta from that second part, all over 1 minus sine of theta as a quantity being squared still on the bottom. I forgot my power of 2 on the cosine, sorry about that. So what's kind of nice is this part right here and here is a trig identity that happens to have a value of 1. So I can group that up, and that would turn into 1 minus sine of theta. And then that would still be over 1 minus sine of theta squared, but that's actually even nicer because one of the 1 minus sine of thetas from the bottom will cancel the entire numerator in this case. So I'm going to go ahead and just say all of this on top will turn into 1 and cancel with one of those, leaving the power of 1 on the bottom. So this now will eventually just turn into a 1 over a 1 minus sine of theta. And that would be my final result unless we wanted to manipulate with some conjugate pairs, but I don't see any real benefit to doing that. Again, that's kind of the trickiest part with any of these trig functions, is there's often a lot of different ways to represent your answer because of all of the trig identities that exist. Letter C is going to be the same general thing. This is just another quotient rule. So I already have the pattern written over here on the left, so I'm just going to follow that same thing once again. See if I can use a little bit more of this white space so I don't have those run into each other as much. So this will be f prime of t equaling, this will be the bottom function, cosine of t, times the derivative of the top, which is just e to the t. Then it's going to be minus the top function, e to the t, times the derivative of the bottom function, which would be negative sine of t. That one's the new one. Then all over whatever the bottom function is, cosine of t being squared, so I could throw parentheses around it, or with trig, usually the best place to put any powers is kind of in between the trig and the angle, or in this case the t. That way it distinguishes as the power is on the function, not just the inside or just on the t. Kind of similar to before, this one has a pair of e to the t's, so I can factor that out. That leaves me cosine of t minus a negative, which switched to addition, was sine of t, and then all of that's over cosine squared of t. It does not seem like I can really reduce anything else, so that would be a good place for me to stop. Okay, moving on to the next example. This one's going to have us do a little bit more than just finding a derivative. We're actually going to need to do an application after the fact. So notice with this one, it's wanting us to, in the end, identify where the tangent line happens to be horizontal. So what I'll need to do is find the derivative and think, because it's a horizontal tangent line, that means my slope or the derivative should equal 0. So I'm going to have to solve, and since this is a periodic type function, it actually will happen multiple times, so we'll likely, as you can kind of see with the example 3 off to the side, we're going to have an answer that probably will resemble something like that, where I have to add or subtract some specific amount, more than likely 2 pi k, maybe even just 1 pi k, but we'll kind of list out the first few examples and see if we can identify a pattern. But anywho, let's go ahead and jump into the finding of the first derivative. So I believe this one we actually have done from earlier, but just treat it like it's a fresh problem. It's going to be just the derivative of x, which is 1, and then derivative of sine is going to be cosine, so 1 plus cosine of x. And again, because we're trying to figure out when it has a horizontal tangent line, I'm just going to set that equal to 0 and solve. So if I just start the solving process by subtracting the 1 over, I get 1 is cosine of x equal to negative 1. And at this point we could think of on the unit circle where that would happen. So cosine, remember, is the x coordinate. So if I were to draw the unit circle, it's negative 1 over here at pi, and then the next time would be at 3 pi, and the time after that would be 5 pi. It's basically every odd pi. So how we would go about doing that is just essentially starting with the x is equal to whatever the first one is, which would be pi. Then it would be plus or minus every 2 pi times, and then just some variable. I like using k to represent it just because that's not a very common variable for us to encounter, so it differentiates itself pretty well. I know they said 2k pi. I read 2 pi k. It doesn't really matter. It's just a matter of identifying that every odd pi, it technically would have that horizontal tangent line. As far as what would the y coordinates be, I guess we could maybe see if there's a pattern happening there. It looks like from our graph off to the right that it's basically every odd pi as well. But we could maybe try plugging it into the original and just see what happens. So let's say I did plug in just pi. F of pi would come back pi plus sine of pi, which sine of pi is 0. So that just is pi. And then let's see, f of 3 pi, see if it just follows that same suit, would equal 3 pi plus sine at 3 pi, also a 0. So yes, it seems to be following a pattern as far as an ordered pair, which I'll go ahead and box up, of my x's. Seem like it's every pi and then every full rotation or period later, and then the y's happen to be the exact same. So that would work as an ordered pair, or if you just said x is equal to y is equal to as two separate statements, that would also technically be satisfactory for a question on a test, for example. If we go ahead and maybe move on to another kind of function, we've got the tangent. So kind of just working through our basic three, sine, cosine, and tangent, and then we'll talk about the other ones. Again, if we needed to have a little proof of why each of these is what they happen to be, you can always do that with one of the difference quotient limit as h goes to 0 type approaches. We could also try doing it as maybe like a quotient rule where it would be sine divided by cosine, since we now have those at our disposal. But again, as far as just what do we need to be able to know and recognize, essentially if we need to take the derivative of tangent, it will always turn into secant squared. So kind of again that similar idea of if the function starts with a c, I know it will be negative. This one, tangent, obviously doesn't start with c, so it stays positive. And you just need to find a way to get committed to memory that tangent and secant will get kind of connected to one another. It is one of the Pythagorean identities that you can kind of have that as one basis for the connection, but again, just kind of a little bit of forcing the memorization, just remembering tangent will always turn into secant squared is one way we can do it. Again, if you forgot it, technically you could switch it to sine over cosine, use quotient rule, and see what it turns into, and eventually it would be a secant squared if you really had to derive it on your own or on the fly on like a test or whatnot. Which is exactly actually what this is going to have us do. I guess I should have read the question. So if I wanted to show that the derivative of that is in fact secant squared, I'll go ahead and mimic that. So first thing it would be is just rewrite it as sine over cosine, since that is equivalent to tangent. That's just the quotient identity for it. And then if we use the quotient rule, I'd end up being able to see that y prime then should equal the bottom function times the derivative of the top function, which would be cosine, minus the top function, which is sine, times the derivative of the bottom function, which is negative sine, and then it's all over whatever the bottom function is, squared. And at this point, we hopefully would be able to see that the top is cosine squared of x. The double negative on the signs make it a positive sine squared of x. Still all over cosine squared of x, which then hopefully we could see that sine squared and cosine squared, or at least remember from one of the Pythagorean identities, is that's equivalent to 1. And then a 1 over a cosine is secant, so a 1 over a cosine squared would be secant squared of, and then whatever the angle is. For this one it was all a bunch of x's, but could be thetas, could be all sorts of different variables. So don't necessarily always think it has to be an x. It can vary from problem to problem. But again, being comfortable with our trig identities, in this case the sine squared plus cosine squared equaling 1, even though it's in a slightly different order, it still has the same value. And then remembering that 1 over cosine is secant, and then just applying or allowing that power to continue on. So to kind of recap, and this is where you might want to take the time to actually pause it. Notice I have everything off to the side here kind of identified, as well as some of the domains of them, since there are some restrictions on them. But as far as just the derivative functions we need to know, we've talked about the first three. The next few that we're going to discuss are like the reciprocals of each. So cotangent, it's happening to have a derivative that's negative cosecant squared. Cosecant turns into negative cosecant times cotangent, and then secant turns into a secant times a tangent. So once again, just to kind of try and show, or at least maybe hammer in that point of if a function that we're starting with starts with the letter c, as cosine, cotangent, and cosecant all do, notice the derivative on the other side does start with a negative in all three of those cases. So that's just kind of one way you can remember which ones need the negative signs, which ones don't. And then from there, it would just turn into what function should I have for that specific thing. So I'll get rid of that just so it's not as busy, but again, maybe take the time to pause, write those down, and these are the things that the expectation will be that we'll get those committed to memory, hopefully before too long. All right, so let's move on to the next example where it's just going to want us to actually apply a couple of things that we've already learned in this unit. Main thing being here, it's identifying a second derivative as represented here by the f double prime. But also the other newer thing in this section, which is let's find derivatives for secant. And this one, it doesn't just want us to figure out what it is, it actually does want us to plug in a value. In this case, it's that pi fourths. So in order to be able to get to the second derivative, we'll have to start with what's the first derivative. So let's just do that, what x is. We're not too worried about the plug-in until we get to that specific derivative. And in this one, it would just be follow the pattern, which you can kind of still see near the top of the screen. Secant's derivative turns into secant times tangent. So secant of x times tangent of x. And now notice if I want to do the second derivative now, I'll actually have to worry about doing a product rule. So hopefully we've seen that enough times, but if I call that a and this b, the first thing I'm going to do is a times b prime, so that would be secant of x. Secant of x times, and then the derivative of tangent of x is secant squared of x. Then it will be plus, this time it will be do a prime, which is secant of x times tangent of x. That's the derivative of secant. Then times the original b, which is tangent of x. So we can likely see that this is really something that we could maybe factor. Looks like they both have a secant, so instead of me combining the secant with the secant squared and making it secant cubed, which I could do, I'm going to go ahead and do this more as like a factor approach. I'm going to take secant of x out front. That leaves me the secant squared of x from this first term, added with, and then the tangent times tangent right here, that's really like tangent squared of x. Why that's kind of nice is actually if I were to try and simplify, maybe to where it's a single function, I could utilize one of the Pythagorean identities for this one as well. I can make secant squared turn into tangent squared plus 1 if I wanted to. That way I would only have to plug into one type of thing. I could also maybe replace it with, what would that be? Secant squared minus 1 is equivalent to tangent squared. But then I still would have secants and tangents to worry about. So I'm actually just going to kind of leave it as is and just substitute in, because after all, this just wants us to figure out what's f double prime of actually pi fourths. And I feel like figuring out what secant and tangent are at that point, which is not overly complex, shouldn't be too terrible. So secant, if you recall, is cosine, but the reciprocal. So if cosine is square root 2 over 2 at pi fourths, so I'll do that kind of off to the side here, sorry. So pi fourths would be this middle angle in the first quadrant. That ordered pair is square root 2 over 2 paired with another square root 2 over 2. But if I take square root of 2 and flip, or sorry, square root of 2 over 2 and flip it, it actually turns into just a single square root of 2. So simplifying, this would become secant of pi fourths. Actually, I'll go ahead and write it out that way. Secant of pi fourths times, and then on the inside, secant squared of pi fourths plus tangent squared of pi fourths is what we need to simplify. Each one of those, if I replace with their value, this would be a square root of 2 outside, square root of 2 being squared for the first term here, and then 1 is technically the tangent at pi fourths, because it's rad 2 over 2 divided by rad 2 over 2, the y divided by the x, and then 1 squared is just going to stay 1. So it looks to me like I just end up with a square root of 2 times, this would be 2 plus 1, which is 3, so why not just call that 3 times the square root of 2. So what does that mean? Well, that means the rate at which my slope is changing, which is actually, I guess in some contexts, if this was a position function to start, then it would have been my velocity as the first derivative, acceleration as the second derivative, so this would be the rate at which my velocity would be changing had this actually had a context to the problem. But with this one, for right now, let's not worry so much about the application of like what does that represent, more just practice the skill of how do I actually find it. This technically would be telling us that it's on a concave up, or the slope happens to be increasing as I'm passing through whatever this ordered pair would happen to be at pi fourths, comma, I guess that would be square root of 2. But again, it's more just, can we evaluate first off what the second derivative is, and then afterwards can we plug the value in and utilize the unit circle to our advantage. At this point, we'll go ahead and move on to the last example, which would be an even more in-depth application here. But one possible thing that could be represented with like either a sine or a cosine wave would be like the motion of a weight on a spring. So if you can kind of picture, like if you pull a spring down a little bit, then let go, that object then will bounce back up and down, up and down, up and down. Now, obviously, eventually it would start slowing down, but initial kind of few seconds, we could probably say that it would stay relatively close to just staying consistent as far as how far up it goes and how far down it goes. So this is not a perfect idea. This would be like if there was no sort of like air resistance, so it could just keep going and going and going. But again, for those that know anything in like physics, this would be like in a vacuum, what would actually happen. So here, as you can see with the context here, we got a 2 meter long spring that happens to be pulled down 1 meter and then released, and it oscillates up and down according to that, and it then follows this pattern as it's modeled by this 2 plus the cosine of t. So it kind of just alternates back and forth between a 1 and a 3 as far as like the how far down from above it happens to be. So how does the length of the spring vary? As you can kind of see, it would just continue to oscillate between those two, but we could try and identify like when is it at its high point or when is it at its low point by figuring out whenever the derivative, which is L prime in this case of t, whenever that equals 0. So in this case it would be at whatever the derivative of that is. So 0 is the derivative of 2, cosine, that would be negative sine of t. And if I set that equal to 0 and solve, that should give me every time that sine is equal to 0, which would be at 0 and then pi and then 2 pi and so on and so forth. It would just continue on and on and on. I don't really have to worry about the negative because, again, context here has time representing, or t representing time, which definitely would have to go in a positive direction. So if I think about what is the position at that, at each of those points, we could just kind of figure out a few of them and just see if there's the pattern that develops. So I would just do L of 0, which would be 2 plus cosine of 0, which is 1, which equals 3. Then what's L at pi? And if I plug in pi, I'd end up with 2 plus cosine of pi is negative 1, so that would actually go back to 1. And then it just keeps going back and forth. So really, how does the length of the spring vary? It has an amplitude technically from its midline of 1 up and 1 down, but it keeps going back and forth between 1 and 3. Now, as far as what is the velocity of that object, the velocity actually was the derivative we just found, so I actually kind of jumped the gun there, but the L of t we could say is the velocity, or L prime of t should be the velocity of this object, and it would be represented by that negative sine of t. So any moment, if I wanted to actually know what the velocity was, it would just be plugging into that expression. So as you can kind of imagine, it'll kind of speed up, or probably be going fastest as it's going through 2, and then as it gets closer and closer to either the top or the bottom, it should be kind of slowing down. As far as just the context of what's going on here. So let's see if it does have anything else specific. Nope, doesn't say any specific time, so I'm going to go ahead and move on. So at what position is the speed of the object a maximum? I'm kind of expecting it to be in the middle, but it should be at whatever time the velocity has its highest acceleration. Or basically we could think on the velocity graph, if I were to do it, it would be at whatever high point that happens to have, or I guess technically low point, because speed as a concept would be positive. So even if it was coming down the page, we would still just make it positive values. So anywho, if we go ahead and figure out what that second derivative is, so L double prime of t would be the same as doing the single prime of the velocity, which again as a concept would be the acceleration. So if I go ahead and do that with that negative sine of t that I just left off with, it would be a negative cosine of t as its derivative. And so if I wanted to then figure out when is the velocity or the speed, which is the absolute value of velocity, when is that positive, I would basically, or when is that its greatest, it should be at whenever the velocity function, the acceleration actually is 0. Because once it's at that point, it would either start slowing down or actually it would have to start slowing down as it goes through there. So if I go ahead and figure out each of those times where this actually equals 0, this one would be at a time of cosine is 0 at pi halves initially. The next one would be down at 3 pi halves. After that, 5 pi halves. So basically every odd pi halves is kind of the pattern that has. So at what position is the speed of the object a maximum? It should be whenever t is pi halves. So we could go back to what position, which is the original. What is L of pi halves? And we'll find that it's probably going to be that 2, but it'd be 2 plus cosine of pi halves, which is 0. So in fact, this does equal at position 2. So every time it goes through 2, it's going its fastest amount. And we could see the same thing if I did the plug in at 3 pi halves, I'd get 2 as well. If I plug in at 5 pi halves, I'd get 2 as well. So every single time it happens to be going the fastest, it would be at one of these odd pi halves, and at the moment when it's passing through a position of 2. All right, next thing is find the acceleration, which technically we already did. The acceleration was everything that we actually just did to come up with that answer. So this would be negative cosine of t. And then at what position is the acceleration equal to 0? We already kind of solved for that right above as well. And that just happens to be when the speed of the object would be at its maximum. So essentially every single time, if I scroll back up so you can see all of that graph, you can kind of see what the kind of how these keep bouncing back and forth between a sine wave and a cosine wave. It's just I end up with some negative signs every time I kind of cycle through this. But at what position is the acceleration equal to 0? The acceleration is going to equal 0 anytime that the t is either pi halves or 3 pi halves and so on and so forth. We already did that work right above. But as far as the position, it would be the position at each of those would be identical. And they'd all equal 2. So it's basically every time it's going through that equilibrium position, that 2, it should be kind of speeding up as it goes and then slowing down, speeding up as it's getting towards it, and then once it gets there, then it starts slowing back down. Then it starts picking up speed again, and as it's going through, it will then slow back down until it gets to the top. So again, every time it's in the middle, hopefully that context and kind of visual, if you kind of think about it, makes sense. Just to kind of point out, there is a little bit more practice at the bottom that might be worth in the notes, just at least checking out. Just some ways that you can utilize the calculator to your advantage. Another example right there. So you notice some of the notation that we've got, this d over dx. You can find it in a couple of places. Probably the easiest way to find it is to do the second, and then let's see, what is that button? I believe it's window. Actually, no, not second. It would be alpha, the green button. My bad. So alpha, then window, has those two buttons to press, and that should give you somewhere in the middle of that list d over dx, or maybe it just says f derive, I think is the notation of it. You can also find it inside of the math menu. So if you just press the math button, which is right underneath the alpha button, somewhere in that list it also happens to exist there as well. That's specific to if you were going through and utilizing TI-84, as you can kind of see from the look of the screen. This one doesn't really show how to do it with the TI Inspire, but if you wanted to have some practice of how we can maybe go about doing this business, more utilizing a calculator, by all means we can. But anyway, hopefully this video has been helpful in at least connecting the dots. Kind of the main takeaways really are, if I scroll back up, just making sure that we have all of these derivatives that were mentioned right there kind of memorized, so that way whenever we see it in the middle of, doesn't matter if it's a power rule and it's a part of like some expression where it's just kind of separate, or if it was a product. Notice we've had quite a few that were just a product rule where part of it I just utilized one of these references. It really wouldn't be much different if we had cotangent or cosecant. So I know I didn't do examples of those ones, but really the approach would be no different. I just need to recognize when I do that, it turns into something else that's specifically connected to whatever that function is. But anyway, hopefully this gets at least most of the things out in the open. But again, if we have questions, we can ask them in class and work through it. Appreciate you taking the time watching the video, and we'll check you later.